So in topology, today we will discuss or study about neighborhood. So we will study a definition of neighborhood. We will read definition of neighborhood and one theorems or examples we will do in this video. So the definition neighborhood. So neighborhood. What is neighborhood? Suppose Xt is a topology space. Xt is the topological space and A subset of A is a subset of X or non-empty subset of X. Xt is a topological space. A subset of X then is said to be neighborhood of a point Xt is a topological space and A subset of X, then A is said to be neighborhood of a point, any point, arbitrary point. This is arbitrary. X belongs to X if there exists G belongs to T, any G belongs to T, such that X belongs to G subset of A. X belongs to G subset of A, and G belongs to T. So element of T, in previous video we have discussed element of T are known as T open sets. It means G belongs to T, it means G belongs to T means G is open set. G is open. G belongs to T means this is open set. X belongs to G subset of means this is open set. This is open set. So A is known as neighborhood of a point X belongs to X. Xt is a topological space, a subset of X. Then A is said to be neighborhood of a point X belongs to X if there exists G belongs to T or open set, or we can say open set such that X belongs to G subset of A. And it is, we write neighborhood like this one. It is written as it is also NB neighborhood of X. Neighborhood, this is NBD means neighborhood. This is short because this spelling is very long, so we will write it short. NBD means neighborhood of X. X belongs to X. Okay? X belongs to A is neighborhood, X belongs to X. So X belongs to G subset of A. It means G is open set. But it doesn't mean A should be open, must be open. A may be open or closed. So by definition, we can say, or if from A, if neighborhood from A, we delete X, means that is A minus X. If we delete X from A minus X is known as deleted neighborhood of X belongs to X. A is called neighborhood of X and A minus X is known as deleted neighborhood of X. Means from neighborhood of X, X is excluded. X is deleted from A. So from the definition, by this definition, we can say So by definition, we can say A must not be, A must not be open. A may be open or closed. A may be open or closed. But every open set and every open set is a neighborhood of point. Neighborhood of a neighborhood of its point. Every open set is neighborhood of its point. This is open set. Suppose this is open set, this is open set, then this is a neighborhood of this points. X belongs to G. So every open set is a neighborhood of its points. It is called open neighborhood. It is called open neighborhood. And neighborhood, it is not necessary. Neighborhood must be open, may be open or closed. And it is known. Every open set is a neighborhood of its point, and it is known. It is known open neighborhood. It is known open neighborhood. So finally, we can say definition of neighborhood means set a subset of X is said to be neighborhood of a point X belongs to X if there exists a open set X belongs to G subset of A, means containing X and contained in A. So this is a definition of neighborhood. Now come theorem. Suppose XT topological space XT is a topological space and X belongs to X is arbitrary. Then X is a topological space and X belongs to X is an arbitrary element of X. So then we have to prove then there exists at least one neighborhood for X belongs to X. If X belongs to X, then there exists at least one neighborhood of X. Second, if n is a neighborhood of X, then X belongs to X. First, we have to prove there exists at least one neighborhood for X belongs to X. At least one neighborhood there exists. Or second is, if n is a neighborhood of X, then X belongs to N. Third, if n is a superset of a neighborhood n of X, then n is also a neighborhood of X. Suppose n is a neighborhood of X and n is a superset of X. n is a superset of n. n is a neighborhood of X. n is superset of n. Then n is also a neighborhood. n is also a means superset of a neighborhood is also a neighborhood. We have to show that superset of a neighborhood is also a neighborhood. And last, fourth one is if n1 and n2 are neighborhoods of X belongs to X, then n1 intersection n2 is also a neighborhood. Means intersection of two neighborhoods is also a neighborhood. Intersection of two neighborhoods also a neighborhood. So XT topological space, we have to show that these four things. XT topological space, X belongs to X as the arbitrary element of X. Then we have to show that first there exists at least one neighborhood for X. Second, if n is a neighborhood of X, then X belongs to n. Third, if n is a superset of a neighborhood n, then n is also a neighborhood. Third, fourth, we have to show that intersection of two neighborhoods is also neighborhood. Means n1 and n2 are neighborhood of X in the same element, then their intersection is also neighborhood. So now we will use the definition. So these are all depends on definition. If we understand definition clearly, then these are very simple. We have to use only definitions here. First is if there exists at least one neighborhood of X. Xt is topological space. What is given? Xt is a topological space and X belongs to X. X belongs to X in arbitrary. So now we can write X T is a topology. Xt is a topological space. X is non-empty set and T is a topology. What is topology? Definition of topology is if T is a topology. T is a if topology. It means phi belongs to T, X belongs to T. Topology. First condition is phi belongs to T, X belongs to T. Second is A belongs to T, B belongs to T. First this one. Second is A belongs to T, B belongs to T. It means A intersection B belongs to T. Third is A alpha belongs to T, means union A alpha belongs to union. So if whatever member is T means T contains X also. Right? Elements of T are known as T open sets. Elements of T are known as T open sets. So here this X, here X belongs to T. It means X is open set. Every element of X is known as, every element of T topology is known as open set T. So this X belongs to T, then this is open set. And we know that every set is a subset of itself. Every set has at least two subsets, phi and X. So we can write this one. X belongs to X, subset of X. We can write this one. Every set is a subset of itself. So what is the definition of topology? Neighborhood. Neighborhood means X belongs to G, subset of A. X belongs to G, subset of A, then A is said to be neighborhood. What is G? G is open set. G is open set. So now compare this one. X belongs to G, subset of A. This is open set. This is open set. X belongs to G, subset of X. So this is A. This is so A is a neighborhood of X belongs to X. So what is A? This A. Hence X is a neighborhood of X belongs to X. So it means if there exists X belongs to X, if X belongs to X is arbitrary, then there exists a neighborhood of X. Always X is always an X belongs to X belongs to X, and X is neighborhood. It means there always exists one neighborhood. It means there always exists one neighborhood of X belongs to X. X belongs to X, you can write subset of X. This is open set. By this definition of neighborhood, here we can prove one. Now comes second. If n is a neighborhood of x, then x belongs to it. Second, let n be a neighborhood of. If n is a neighborhood of x, then we have to show that x belongs to n. Now definition, we will use definition, same definition. N be a neighborhood of x belongs to x. What is n? Here, this is n. This is n. So by definition, what is the definition of neighborhood? Definition, there exists G belongs to T such that x belongs to G subset of n. This is n. X belongs to G subset of n. So if n is a neighborhood of x, then there exists G belongs to T or open set such that x belongs to G subset of. So if x belongs to G, and G is a subset of n, then x also belongs to n. Means x belongs to G and G subset of n, then x belongs to G subset of n means all elements of G belongs to n. All elements of G are in n. So x belongs to G, it means x belongs to n. So this is x. Then if n is a neighborhood of x, then x belongs to n. So now come third. It is very simple. We have to use only definition. We use here definition only. If n is a superset of a neighborhood n, means n is a neighborhood of x. First we suppose. Third, let n be a neighborhood of x belongs to x. N is a neighborhood of x belongs to x. So definition, same definition. It means then there exists G belongs to T such that x belongs to G subset of. This is the definition of neighborhood. Let n, if n is a neighborhood of x, then x belongs to G subset of. Now M is superset. Superset means it contains n. Okay, all elements of n are in M. Now M is superset of n. N is superset of n. It means n subset of n subset of n. Now from these two, these two, x belongs to G subset of n subset of n. We can write x belongs to G subset of n subset of n. X belongs to G subset of n subset of n. We can write this. It means x belongs to G subset of n. X belongs to G subset of n. G is open. G belongs to T. G is open. So x belongs to G subset of n. It means n is a neighborhood. It means n is a neighborhood of x. So if m is a superset of neighborhood n, then m is also neighborhood. Now intersection of two neighborhoods. Now we show that intersection of two neighborhoods. Four. N1 and N2 are neighborhood of x. Means N1 is a neighborhood of x belongs to x. It means there exists G1 belongs to T such that x belongs to G1 subset of. This is the definition. We will take G1, G2 open set. Now N2 is a neighborhood of x belongs to x. same element. It means then there exists G2 belongs to T such that X belongs to G2 subset of N. So X is the same element, X belongs to G1. We can write X belongs to G1 subset of N1. X belongs to G2 subset of N. G1, G2 belongs to T. G1, G2 belongs to T. G1 and G2 is a topology. Because T is a topology, it's an open set. G1 and G2 are open set. So X belongs to G1. X belongs to G2. Means X is common in G1 and G2. It means X belongs to G1 intersection G2 subset of N1 intersection. Okay? And G1, G2 belongs to T. G1, G2 belongs to T. T is a topology. So what is the definition? Second condition of topology is A belongs to T, B belongs to T, A intersection B belongs to T. It means A, this is B, A belongs to T, B belongs to T, A intersection B belongs to T. It means G1 intersection G2. This is open set. This is open. So X belongs to G, X belongs to G subset of A. So this is in the form X belongs to G subset of A. G is open. This is open. So this is A is a neighborhood of X. A is a neighborhood of X. So what is A? This one. This is a neighborhood of X. It means N1 intersection N2 is a neighborhood of X. So we suppose N1 and N2 are neighborhood of X, then N1 intersection N2 is also a neighborhood of X. So if X belongs to X, T is a topological space, X belongs to X, then there exists at least one neighborhood for X belongs to X. If N is a neighborhood of X, then X belongs to N. If M is a superset of N, then neighborhood N, then M is also, means in superset of a neighborhood is also a superset. We will use here in definition or in example, then we will use this one. Superset of neighborhood is also neighborhood, or intersection of two neighborhoods is also neighborhood. So we'll take example, one more example of here. Let's suppose X is equal to 1, 2, 3, or we can say A, B, C, D. And T is a topology. A, B, C, D is X. X, T is topology is where what is T? Phi X. T has added T topology T, phi belongs to T, X belongs to T. These two must be in T. And suppose other is B, A, B, or A, B, T. So this is suppose topology space. Now we have to find neighborhood of A and B suppose, or A, B, C, D you can take. So we will find neighborhood A and B, and C, D you can find by the definition we will use here definition. So first neighborhood of A. So what is the definition? Neighborhood of A. A set A belongs to means X belongs to G subset. G is open set. So open set means elements of T are open set. Elements of T are open set. So these all are open sets. So containing open set containing X containing A. So first we will find T open sets containing X. T open sets means this G. T open sets means G containing X containing A containing A here. X is A. X is A. So what is the open sets containing A? Open sets containing A. First this one. X means this one. A B C D. So X here is not A, here AB and AB. These are open sets. And A may be, this is neighborhood. Neighborhood may be open or closed. It doesn't necessarily must be open. So we know that first thing, and then we will use the third condition also, the theorem we have proved before. Superset of a neighborhood is also superset. So these are the neighborhood because every open set is a neighborhood. Every open set is a neighborhood by definition, we know. So these are neighborhoods, and if we find superset of this, superset of a neighborhood is also superset. So superset of X, superset of X is superset of X means X subset of X. X only X contains X. We can say X subset of. Now superset of AB. Superset of AB means sets containing AB. So what containing AB? First X. X containing AB. X is ABC. Now what is AB? AB set itself also. AB is also AB. And this is AB. 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 And ABC also contains ABC. ABC. ABC also containing AB. And ABD, ABC and ABX. These are superset of AB. Now superset of ABD. Superset of AB means one set itself, one is set itself, ABD, and other one containing ABD. Which contains ABD? ABD means X. X contains. So these are the supersets. So every superset is also neighborhood. So neighborhoods of A, neighborhoods of A are. What are the neighborhoods of A? We'll take here the common all things. So first X, then AB, ABD, ABC. All sets we write here. If sets coming 2-3 times, we will write 1 times. Okay. All sets should come here. Must come here. X, AB, ABD, ABC, ABD also here. So these are the neighborhoods. Similarly, we can find neighborhood of B. Suppose neighborhood of B. We can find neighborhood of B. B. T open sets containing B. So what are containing B? Is X containing B, B containing B, AB containing B, ABD containing B, ABD containing B. So all these open sets containing B. Now same thing, superset of X. Superset of X is equal to superset of X is X. Now superset of, we will write here, superset of ABD. Superset of ABD, one set is itself ABD, AB, and another is X. X also contains this one. And superset of AB, superset of AB. One is AB itself, then ABC, then ABD, then X, and ABC, ABD, X. Now superset of B, what are the supersets of B? What sets containing B means one is B, AB, BC, ABC, ABD, BCD, ABD, BCD, ABC, X, or maybe you can check B, AB, BC, C and CA. There is no B, so we do not include CA here. ABC, ABD, okay. So these are the supersets. So neighborhoods of B. So neighborhoods of B is, so all sets will write one time. Okay. So B, BC, AB, BC, ABD, ABC, BCD, X. So these are the neighborhoods of. So like this, we will find neighborhood of a point. First, we will find open set, T open sets containing the element. Then we will find superset. Whatever sets containing that element is also, because every superset is also neighborhood of. Because every superset of neighborhood is also neighborhood. So the definition and the theorems we will discuss here is very, very important to understand basically things of neighborhood. So in next video we will discuss more about some closed set, open set, and some examples